the previous lecture, I have introduced the topic of counting, and we discussed little bit of historical aspects of it, that is how the subject developed over the past few centuries, and then we started discussing the fundamental principles of counting. The first principle was the addition principle, which simply says that if there are a number of ways of doing one type of thing, there are several number of ways of doing another thing, then what is the total number of ways doing either of them. So, it is simply adding. The second fundamental principle of counting is called the multiplication principle, in which we are sort of looking at the simultaneous occurrence of two different events. So, if one event occurs in m ways and another event occurs in n ways, then in how many ways both of them occur together. That means, either we say first occurs, then the second occurs, or the second occurs, then the first occurs, or it could be exactly simultaneous also. So, then it becomes multiplication, that is the total number of ways is m into n. So, let us continue looking at some of the examples to illustrate this thing. So, the next problem is like this: how many six-digit natural numbers can be formed whose first and third digit is not first, rather fifth and third digit is odd, and remaining digits are even. We assume that 0 is also even, because 0 can be a digit here. So, we assume 0 to be even here. So, let us look at the solution. So, the first digit is even. So, there are possibilities 2, 4, 6, 8, that is 4 ways are there. Okay. The first digit cannot be 0, because we are saying 6 digit numbers. So, therefore, first digit cannot be 0. So, since we are saying it has to be even, because we have put the condition the third and the fifth digits are odd. So, first, second, fourth and sixth digits, they are even. So, the first digit even can be chosen in 4 different ways. Then the second, fourth and sixth digits each can be from either of 0, 2, 4, 6, 8. That means 5 into 5 into 5 ways. So, I have applied the multiplication principle here, that is the second digit can be chosen in 5 ways, the fourth digit can be chosen in 5 ways, and the sixth digit can be chosen in 5 ways, and all of them have to be together. So, therefore, 5 into 5 into 5 ways. Now, let us look at the third. The third and fifth digit each can be either 1, 3, 5, 7 or 9. That means, 5 different ways of choosing the third digit and 5 different ways of choosing the fifth digit, that is 5 into 5 ways. So, now we have fixed the first digit can be chosen in 4 ways, second, third, fourth, fifth and sixth, each of them can be chosen in 5 ways. So, the total number of ways becomes So, total number of such 6 digit numbers is 4 into 5 to the power 5. Of course, you can multiply it out and then see the answer is 12,500 such numbers are there. Let me just repeat or review the problem. There are 6 digits, we wanted to choose this 6 digit number in particular fashion. So, we said that the third and the fifth digit is odd and the remaining digits are even. If we do that, then in order to choose the first digit, we have to choose out of 2, 4, 6 and 8. So, there are total number of ways is 4. Now, for the remaining, each of them can be chosen in 5 different ways. So, therefore, the 5 digits, that is the first, the second, third, fourth, fifth and sixth digits, they can be chosen in 5 to the power 5 ways. So, therefore, the total number of possibilities is 4 into 5 to the power 5. That is, there are total such 12,500 numbers. Let us take another problem. In a mathematics conference, there are n mathematicians. It turns out that each mathematician discussed with every other mathematician in the conference exactly one problem. So, how many problems were discussed? So, each one discusses with n minus 1 other mathematicians. There are total n mathematician, each one discusses with the other n minus 1. So, it becomes by multiplication principle n into n minus 1 problems. Now, in this particular counting, every person is counted twice, because for example, if I say mathematician A discusses with mathematician B, then I have counted it once. Now, again I am saying mathematician B discusses with mathematician A. So, that will be 2 times, whereas I am putting the restriction that each one discusses with another one exactly one problem. So, that means, now each person is counted twice in n into n minus 1. So, we will have to divide by 2. However, here everyone is counted twice. So, we have actually applied the multiplication principle, but with little bit of modification in this particular problem. Let me solve another such problem. How many 10 digit telephone codes can be created where the first two digits are 9 and 4 and the third digit cannot be 0. So, if you look at this, the first place is fixed as 9. So, first digit exactly one way. For the second digit, you are fixing as 4. So, now the third digit is not 0. So, the third digit can be from numbers 1, 2, 3 up to 9. So, 9 ways, and fourth place up to 10th place you can have either of 0, 1, 2 up to 9. So, there are 10 ways each. So, now these are 7. So, by multiplication principle, so by multiplication principle, the total number of codes is 9 into 10 to the power 7. How many distinct terms are there in expressions? For example, if I consider say x plus y plus z plus t into say a plus b plus c plus d plus e, or say I consider x 1 plus x 2 plus x m, y 1 plus y 2 plus y n, z 1 plus z 2 plus z t. Now, you can consider, see, if we look at the product here, it is nothing but looking like very similar to a Cartesian product of two sets, in which the first set has 4 elements and the second set has 5 elements, because each term will appear with each term in the second case exactly once. Like you will have x a plus x b plus x c plus x d plus x e. Similarly, then with y a, y b etcetera, and finally, t a, t b, t e etcetera. So, this is exactly acting as a Cartesian product of two sets. One is consisting of 4 elements and the other is consisting of 5 elements. So, in the first case, the total number of terms is exactly the same as in the Cartesian product A cross B, where is 4 and Cartesian product cardinality of B is 5. So, cardinality of A cross B is nothing but 4 into 5, that is equal to 20. So, if we extend this argument to the second part of this problem, in the second part, then you can see, if I consider the set E 1 consisting of m elements, the set E 2 consisting of n elements, and the set E 3 consisting of t elements, then it becomes nothing but the product of E 1 cross E 2 cross E 3. So, following the reasoning given in 1, we can say that the number of terms is m into n into t. Now, let me introduce the next notation, that is called factorial notation. So, the notation n factorial represents the product of the first n natural numbers, that is n factorial is equal to 1 into 2 into 3 into n minus 1 into n. So, for example, we say 1 factorial is equal to 1, 2 factorial is equal to 1 into 2, that is 2, 3 factorial is equal to 1 into 2 into 3, that is equal to 6, and so on. As a convention, we define 0 factorial to be 1. This is to keep consistency with some other notations of permutation and combination that I will be using later on. In that, it will turn out that if we take 0 factorial to be 1, then the consistency of the notation will remain. Also, we do not define the factorial of a negative integer. So, it is only for basically positive integers, and we include 0 factorial as a special case. Now, something very simple you can observe, see this n factorial is equal to n into n minus 1 factorial. I had mentioned in the beginning about the historical development of the combinatoric subject. There are indications that actually this notation was also known to Indian mathematicians, that is the continuous product of natural numbers. However, they did not use the notation n factorial etcetera. This notation n factorial is actually introduced in 1808 by Christian Kramp. There are indications that ancient Indian mathematicians knew the concept of product of consecutive natural numbers. The modern notation was introduced by Christian Kramp in 1808. What is important to observe about this number, this notation? So, for example, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. You can see that it increases very rapidly. So, let me just illustrate it. we can note that n factorial increases very rapidly as n increases. So, for example, if I consider say 4 factorial, it becomes 24. If I consider 5 factorial, then it becomes 5 into 4 factorial, that is 120. 6 factorial becomes 6 into 5 factorial, that is becoming 720. Then 7 factorial will become 7 into 720. So, you can immediately see that number is increasing very fast. By 7 factorial, we have come to 5040. And then again you can see, if I put 8 factorial, then again I have to multiply by this by 8. So, I will get into something like 40,000 plus something. So, that is 4 into 10 to the power 3 kind of thing. And then again if you say 9 factorial, 10 factorial, the number is increasing very rapidly. However, this factorial notation is one of the very you can say important parts of the current mathematical terminology, and in every aspect, whether you are doing probability theory, whether you are doing combinatorics or you are doing calculus, there everywhere this factorial notation is widely used. Now, using this we come to the next term, that is called the permutation. So, what is a permutation? An ordered arrangement of k distinct elements from a set of n distinct elements is called a k permutation. The total number of all k permutations is denoted by the notation NPR, NPK. Sometimes it is also written like this NPK. So, in various books you will see various notations. I will be using this notation. Now, let us see what would be the value of this. That means, if we have a set consisting of n distinct elements, then how many ordered arrangements of k distinct elements from there can be taken. So, please note here I am talking about ordered arrangements. Suppose I say n is equal to 3. So, suppose I say A, B, C. Suppose I am considering 3 elements here. Suppose this is the set A, and I want to choose say 2 here. So, I can choose A B, I can choose A C, I can choose B C, but if I am looking at the ordered arrangement, then I will also count B A, C A and C B. So, total such arrangements becomes 6 such cases. So, in general, if I am choosing k ordered things from n, then how many? So, I have given the notation NPK. Let us calculate this thing. In order to evaluate NPK, we can proceed as follows. The first element can be chosen in n ways. The second element can be chosen in n minus 1 ways and so on. The kth element can be chosen in n minus k plus 1 ways. So, now you apply the general multiplication principle. So, by the general multiplication principle, the total number of ways is n into n minus 1 into n minus 2 and so on up to n minus k plus 1. So, that is n p k. So, we have developed the formula for n p k. Okay. We can look at this. So, this we can write actually n p k as n into n minus 1 and so on up to n minus k plus 1, and I consider multiplication by n minus k minus 1 up to 3 to 1, and then divide by the same number, that is n minus k into n minus k minus 1 and so on up to 3 to 1. Then this number is nothing but, if you see, the numerator becomes n factorial and the denominator is n minus k factorial. So, that is n p k has an alternative expression n factorial divided by n minus k factorial. In order that this is well defined, you should have 1 less than or equal to k less than or equal to n. This makes sense to have actually n also included here. That means, if you choose all n, then how many such things will be there? It will become n factorial. So, let me just illustrate this again. So, if we consider all possible arrangements of n distinct elements, then that will become equal to n p n, that is n factorial divided by n minus n factorial, that is n factorial divided by 0 factorial, that is n factorial, because 0 factorial I am taking to be 1. So, for example, if I consider two elements a and b, then the number of ways will be a b b a. So, that means 2 or 2 factorial. If I consider 3 a b c, then it will become a b c, a c b, b c a, b a c, c a b and c b c. Therefore, total number will become 6, which is nothing but 3 factorial, because 3 into 2 into 1. If we allow the repetition, then the answer will change. So, the number of permutations of n different objects taken k at a time, where repetition is allowed, is n to the power k. Because in the first place I can consider n, in the second place any n, because repetition is allowed. So, n into n k times. So, it becomes n to the power k. Now, if we consider here, I have considered this all n items to be distinct, but there is a possibility that some of the items may not be distinct. So, in that case this formula can be modified the number of distinguishable permutations of n objects of k different types. For example, where n1 objects are alike or similar, basically they should be of same nature actually. So, let me not write similar, alike, n2 are alike and so on, nk are alike, and you have n1 plus n2 plus nk is equal to n. Then the number of distinguishable permutations is n factorial divided by n 1 factorial, n 2 factorial and so on, n k factorial. Let me explain the reasoning. I consider that if we have all possible arrangements of n distinct elements, so it is n factorial. Now, suppose out of this n objects 2 are similar or alike and remaining n minus 2 are distinct. Now, if we are considering any positions where these two items which are alike appear, then in whichever order they appear it will not be distinguishable. So, that means, if I am counting them 2 times in n factorial, then I should divide by 2. So, the answer will become n factorial by 2 factorial or 2. Similarly, if I say 3 items are similar, then those 3 items wherever they appear in whichever order, that order will not matter because they are similar or alike. Now, we have counted them 3 factorial times, that is 1 into 2 into 3. So, the number will become n factorial divided by 3 factorial. So, now if we extend this argument, then if n 1 things are same, then we should divide by n 1 factorial. Then another n 2 type of things are same, then we should divide by n 2 factorial and so on. Finally, when n k things are same, then those n k factorial things also have to be divided, because the number of ordered arrangements is same as the unordered arrangement, because here that ordering or unordering does not make any difference, because all of the items are alike. So, for example, just I show through a live thing. So, these 2 pens are there. So, you can see here they are alike. So, whether I put this here and this here, or I put this here and this here, it does not make a difference. But if I consider this blue and this black, then if you see, if I put this first and this here, that is the left and right, and if I change the order, then these are 2 different arrangements. So, now if you consider 3, now if I have 3 distinct things, so let me just take these 3 distinct things, then I can have 1, 2, 3. So, that is I can put this here, this is another arrangement, I can put this here, this is another arrangement, and this I can put here, this is another arrangement. Then I can put this here, this is another arrangement, and this I put here, this is another arrangement. So, total 6 arrangements are there, but if 2 of them are alike. So, if I take this, now let us look at how many arrangements will be there. This is here or this is here. So, there are total 3 arrangements now. 3 distinct arrangements are there. Why? Because this 2 in whichever order you keep, it does not make any difference. So, that means 3 factorial has been divided by 2, that is 6 divided by 2, that gives you the answer 3. So, therefore, you have this general formula, that means, if I have n distinct items, out of which n 1 are alike, n 2 are alike and n k are alike, then the total number of distinguishable permutations is n factorial divided by n 1 factorial, n 2 factorial and n k factorial, that is coming in the denominator. So, I hope I have made the explanation very clear. Let us look at some examples here. How many different ten-letter codes can be generated using 2 A's, 3 B's, 2 C's and 3 D's. There are total 10 letters available with me, that is 2 A's, 3 B's, 2 C's and 3 D's. So, total 10 numbers are there. As you can see here, there are 2 of A's. So, in whichever order I put, it will not make any difference. There are 3 B's, in whichever order I will put, it will not make any difference. Similarly, about 2 C's and similarly about 3 D's. So, the total number of arrangements by this formula will be distinct codes, that is 10 letter, all 10 are used here, that is equal to 10 factorial divided by 2 factorial, 3 factorial, 2 factorial, 3 factorial. So, after some simplification, this number can be evaluated, it is 25,200 codes that are possible. Let me take another problem here. How many words can be made using all letters of the word nation? Okay. So, let us look at this. If I have to use all the 6 letters, then you look at how many are distinct. Here there are A, I, O, N and T, that is occurring. So, 5 distinct letters is there, out of which N is repeated once. So, here we have 6 letters where N occurs twice. So, the total number of arrangements of these 6 letters by the formula, it will become 6 factorial divided by 2 factorial. So, that is equal to 360. Similar problem, let me look at how many distinct 11 letter arrangements of the word probability can be made. So, you can see here in probability we have 11 letters. So, total number of letters is 11. Out of this, if you observe, B occurs twice and also I. This I also occurs twice. So, the total number of arrangements by this formula, it will become 11 factorial divided by 2 factorial into 2 factorial. This number can be evaluated. It is 99 lakhs 79,200. As you can see here, this 11 factorial is a huge number. So, that is 4 times of this, which we divided by 4. So, we are getting. So, it is actually already coming in tens of millions actually. So, that is the nature of this number factorial. It increases very rapidly. Now, in this itself, if we observe in the probability, there are some vowels and some consonants are there. So, suppose we want to look at that arrangements also. So, let me just pose a problem here. In how many of these arrangements say vowels appear together? So, let us look at this. Here we are having seven consonants in which B is repeated twice. Okay. So, now if we consider all the vowels to be together, that means whenever they occur they appear together, then actually there are basically 8 items here, that is the 7 consonants and all the vowels are together. So, we can treat this as one item. Since all 4 vowels where I is repeated have to appear together, we have total 8 items. So, the number of arrangements is 8 factorial divided by 2 factorial, because B has been repeated. Now, there is a catch here. These vowels, although they are taken together, but they can permute among themselves. So, therefore, how many such arrangements are possible? Since vowels can be permuted among themselves, such arrangements are 4 factorial divided by 2 factorial, because I has been repeated here. So, that is nothing but 12. So, now the final number will be equal to total number of words from the letters of word probability where vowels occur together, that will become 8 factorial divided by 2 factorial into 12. So, of course, you can evaluate it, it is equal to 24 2,41,920. What we have done? We have calculated all the words which are created from the word probability. We have also calculated the arrangements where the vowels appear together. So, there is an additional problem you can solve from here. Suppose we say vowels do not appear together. So, in how many of these vowels do not appear together? Then it will be from total number of arrangements minus the number of arrangements in the which the vowels are together. So, you take the answer of question number 3 minus the answer of question number 4. So, that number will become 99,79,200 minus 2,41,920, that is 97,37,280. So, let me just solve another problem of similar nature. In how many ways letters of the word say towel can be arranged so that all vowels occur together and all consonants occur together. So, let us observe this. How many consonants are here? There are 3 consonants, all are distinct, that is T, W and L. Similarly, there are 2 vowels O and E. So, they are also distinct. So, basically if I am saying all the consonants appear together, then it is treated as one entity, and 2 vowels occur together, then that is also considered as one entity. So, basically arrangement of them can be either firstly all the consonants, then all the vowels, or reverse of it. So, basically 2 possibilities are there, but now you look at these consonants themselves can be permuted and they are all distinct. So, there are 3 of them. So, it becomes 3 factorial. Similarly, all the vowels can also be permuted among themselves. So, that is 2 factorial. So, you will have the number of ways will be 2 into 3 factorial into 2 factorial. So, that is equal to 24. So, there are total 24 letters of T O W E L, where all the consonants appear together and all the vowels appear together. So, let me just repeat here, in the topic of permutations, we are actually looking at the ordered arrangements of the items. That means, if I am considering positions, then they have to be fixed. If I interchange the positions of the items, then it is considered another arrangement. Now, if we exclude that thing, that means, if I consider this arrangement and this arrangement as the same, that means, I consider unordered arrangement, then it is called combination. So, I give a new definition now. An unordered arrangement of k distinct items from a set of n distinct items is called a k combination. The total number of all k combinations is denoted by n c k, or there is another notation popularly used n c k. Sometimes it is written as n c k like this also. So, in various books you will have different notations. I will generally use n c k like this or like this. Again you can see here 1 is less than or equal to k, less than or equal to n. Now, let us find out the value of this. In order to evaluate, say x, that is equal to n c k, we proceed as follows. So, if we consider the ordered arrangements, there are n p k. The number of ordered k arrangements is n p k. Now, for these k things, there are k factorial such things, but now if we say that ordering is not important, then all of these things will be considered same. So, for example, if I say A B, so A B and B A, they are distinct if I am considering ordered permutation, but if I consider unordered, then A B and B A are the same. So, that means, you have to consider number as 2 divided by 2. Similarly, if I consider 3 things, so A B C, B C A and so on. So, I have 3 factorial such things. Now, I will be considering all of them as 1. So, I have to divide the number as divided by 3 factorial. So, if I look at this, there are k factorial permutations. Now, all of this will be considered same. So, of these k objects. So, you should have n p k divided by k factorial is equal to x, that is n c k. So, this is the formula that now you got. N c k is nothing but n p k divided by k factorial. So, this implies that n c k is nothing but n factorial divided by k factorial n minus k factorial. In fact, I can consider 0 also, because 0 factorial we have defined. A historical note is that historically this type of formula appears in the work of Indian mathematician Bhaskaracharya too. His timeline is around 1114 to 1185 AD. Let us look at some of the properties of this combination. Actually, this terms NPK and NCK, they have lot of relations and there are several properties. So, I will cover some of these here. So, for example, NCK is equal to NCN minus K. The proof is extremely simple because it is just based on what you are writing. So, NCN minus K is equal to n factorial divided by n minus k factorial n minus k factorial, that is equal to n factorial divided by n minus k factorial into k factorial, which is nothing but again n c k. So, friends, actually we have discussed 4 major counting principles. One is the fundamental principle of addition, second is the multiplication principle, third one is the total number of ordered arrangements, that is we are denoting by permutation NPK, and the fourth one is the number of unordered arrangements, that we are denoting by NCK. In the next classes, I will continue to describe the properties of this and various problems that are based on this. I will be solving in the next few lectures.